From world-building AIs that can reconstruct and simulate 3D environments from text, images, and video, to recurrent language models that finally tame instability with new scaling laws, and autonomous driving systems that learn to balance safety and efficiency through generator-discriminator reinforcement learning, today's papers push AI into more grounded, stable, and intelligent territory. In this episode, we'll explore how these breakthroughs reshape perception, reasoning, and real-world decision-making, and why they may define the next wave of practical AI systems. Let's explore the first paper, HY World 2, a multimodal world model for reconstructing, generating, and simulating 3D worlds. HY World 2 is a unified open-source multimodal world model that bridges 3D world generation and reconstruction from text, single images, multi-view images, and video. For sparse inputs, it generates navigable 3D Gaussian splatting worlds through a 4-stage pipeline: HY Pano 2 panorama synthesis, world nav trajectory planning, world stereo 2 keyframe expansion, and world mirror 2 composition. HY Pano 2 replaces explicit camera warping with an MMDeep-based latent perspective to ERP mapping using hybrid real panoramas plus Unreal Engine renders and seamless circular padding plus pixel blending. WorldNav parses panoramas with Moge 2, Quinn 3, VL, SAM 3, and recast navigation. Then plans 5 path types: regular, surrounding, reconstruct aware, wandering, aerial optimized for coverage and collision avoidance. World Stereo 2 abandons spatiotemporal video VAE compression in favor of a keyframe VAE, adds explicit camera control via pluck arrays and point clouds, and introduces 2 memory modules: Global Geometric Memory and SSM++, which uses selective retrieval, horizontal stitching, and modified ROP. After DMD distillation, it runs in 4 steps. World Mirror 2 is a feed-forward geometry backbone with normalized ROP for resolution generalization, depth to normal supervision, and a depth mask head. It supports token budget dynamic batching, BF16, FSDP, sequence parallelism, and multi-prior prompting. The final 3 DGS stage aligns generated depths to panoramic point clouds via ransack linear calibration and mass Gaussian pruning, reducing Gaussian count by 73.7% with only 0.14 decibels PSNR loss. Results report state-of-the-art performance on open-source benchmarks and competitiveness with Marble. In reconstruction, World Mirror 2 improves high-resolution real estate 10K camera, AUC at 30 from 66.29 to 86.89, and ScanNet normal mean error from 17.6 to 12.5, while the full pipeline completes a world in about 712S on NVIDIA H20. Let's explore the second paper, Parquet Scaling Laws for Stable Looped Language Models. Parquet studies looped language models as dynamical systems and identifies the main training failure mode in prior recurrent depth models as residual stream instability caused by unconstrained injection matrix spectra. Recasting the loop update as HT plus 1 equals AHT plus B plus RHTE. The authors linearize to an LTI system and show that prior addition-based and concatenation-based injections correspond to marginally stable or unstable A, with divergent runs learning row A, G, 1. Parse fixes this by discretizing a continuous parameterization and constraining A to a negative diagonal form, guaranteeing row A is less than 1, plus normalizing the prelude embedding and switching to per-sequence depth sampling. These changes eliminate residual explosion and late training loss spikes, while adding only 0.350.83% parameter overhead relative to matched transformers. Empirically, Parse lowers validation perplexity by up to 6.3% over prior large-scale looped models, and on a 1.3 B parameter run trained on 100 B tokens, it improves core and core extended by 2.99 and 1.18 points over strong transformer baselines, reaching 87.5% of a transformer twice its size. Under matched parameter budgets, a 770 M parse matches or exceeds a 1.3B transformer on core. The paper's main scaling result is that looping is an orthogonal compute axis. In isoflop training, optimal recurrence, mu, rec, and token count both follow power laws with exponents near 0.4 and 0.78, respectively. At test time, quality improves with recurrence according to a saturating exponential decay, LT equals L, infd plus Z, Z, T, And the unified law, LT, mid, mu, rec, d, predicts held-out curves within 0.85 1.31% error, confirming that training depth sets the inference time ceiling. Let's explore the third paper, RAD2, Scaling Reinforcement Learning in a Generator-Discriminator Framework. RAD2 reframes end-to-end autonomous driving as a generator-discriminator RL problem. A diffusion-based generator proposes multimodal future trajectories, while an RL-trained discriminator re-ranks them using long-horizon, closed-loop quality rather than sparse rewards on raw trajectory coordinates. This decoupling stabilizes optimization in a high-dimensional continuous action space, which is the paper's central novelty. To reduce credit assignment noise, it introduces temporally consistent group relative policy optimization, TCGRPO, which reuses a selected trajectory over a fixed execution horizon and computes group relative advantages across temporally coherent rollouts. To move the generator toward better behavior without destabilizing diffusion training, on-policy generator optimization, OGOZ, converts closed-loop feedback into structured longitudinal edits, effectively shifting acceleration, progression, while preserving spatial path geometry. The system is trained and evaluated in BEV Warp, a feature-level, closed-loop simulator that spatially warps bird's-eye view features instead of rendering images, enabling high-throughput interaction. Validation is also reported in a photorealistic 3D Gaussian splatting environment. On the BEV Warp benchmark, RAD2 cuts collision rate from 0.533 for ResAd to 0.234 on safety-oriented scenarios and improves safety at 1 from 0.418 to 0.73, while raising EP mean from 0.97 to 0.988 and EP at 1 from 0.516 to 0.736 on efficiency-oriented scenarios. Against Senna, 2 on open-loop Senna, 2 evaluation, it reduces FDE from 0.597 m to 0.553 m, ADE from 0.225 m to 0.208 m, and CR from 0.288% to 0.142%. Ablations show that joint generator, discriminator optimization, discriminator initialization from the planning head, entropy regularization, and a group size of 4 are all important for the final safety efficiency trade-off. That's a wrap on today's AI paper highlights. Thanks for watching.